So here we are going to discuss about authentication or identification, identity. Authentication is all about telling who you are, proving who you are. It's all about proving your identity. There are a lot of challenges around it, mechanisms, trade-offs, all these OTPV type, multi-factor authentication. All these are related to the topic we are discussing, proving your identity. So that's what we are going to discuss. Let's get into the topic. Let's start by assessing where we are regarding our training and what we have learned so far, what we are trying to get at, and things like that before we go with anything concrete. So we have discussed about the two pillars. So one pillar being the cryptography. Then there is this other pillar which we are yet to discuss. Let's put question mark here. That's not discussed so far. We've been discussing cryptography, and in cryptography we discussed hashing, then symmetric encryption and RSA DH, although they are completely different. Even the purpose is different. I'm going to keep it in the same place in terms of algorithm. Then we talked about DS or digital signatures, very important topic with hashing and RSA. DH is not really used for digital signatures. You need public key to verify the signature. And finally, combined all these things, digital signature, symmetric encryption, and RSA or DH for key exchange, we discussed the mighty TLS. So we have gone through a lot of details of TLS and rest of the things. Now we are in a good position to discuss a lot of things, mainly authentication, authorization, role-based access control. So authentication, authorization. So authorization is to determine what an authenticated person can do in a system. Then role-based access control or RBAC, which is very closely tied with authorization. Authorization and RBAC is kind of more or less different sides of the same coin. Also, we can discuss different techniques used for these things like SAML, then OIDC, all this kind of related and current technologies or protocols, in fact, we can discuss. In fact, all of them are based on one of these principles we have learned. So if you have understood all these basics we have learned so far, in fact, you don't have to follow the rest of the training to understand any of these things. If you look at the documentation, in fact, if you look at the image of SAML, you will understand SAML because all it is doing is exact same verification in a different way. SAML and OIDC is just different industry name for exact same underlying technology used in slightly different context, but we will see both. But at the end of the day, from our discussion perspective, they are just one and the same thing, although from business perspective, they are different. So to discuss something like role-based access control, we need to get into concepts like object, then some calls towards the object, then policies, trust relationship, policies/permission. So there are few related things we will discuss as and when it comes. So this particular lesson is all about concepts and general pattern. These names right here, I'll be using those names in a general way. You need to understand that. After that, we will get into specific companies' technology. For example, AWS IAM. It's kind of a typical implementation of this whole thing if you're talking about. Same with Azure AD. So we'll be looking into some of the examples of Azure AD and AWS IAM to understand how these things are implemented in the real world. But some of the names, especially, for example, object can mean slightly different things. Service principal, objects, principles, resources, all these things can mean slightly differently in different platforms. But ultimately, it's all boiled down to the principle or patterns we are going to look here in this particular lesson. But in this lesson, we'll look at in a generic way. We'll not tie ourselves into certain platforms. But when we discuss specific patterns, for example, roles in AWS, or pretty much almost all the cloud has a name roles, which is fairly a new terminology. It was groups in earlier Active Directory days. So such kind of terminology difference will be there, but the concepts we will discuss here. So another thing I mentioned is the users or groups, roles, all these kind of things we will discuss when we discuss role-based access control. So what we can do is start with authentication. What's the concept of authentication? So let's erase this particular diagram and look into authentication. So in this lesson, we are continuing with authentication. I'm pretty sure you have done this at least once for sure, at least to log into the platform in which you are watching this video right now. At the end of the day, the simplest example is username and password. So this is probably one of the oldest type of authentication, username and password. Then you can have fingerprints. I'm going to put it FP, fingerprint. Then face, other biometrics like iris, biometrics. Then PIN, patterns, all sorts of different things. Now, what all these things have in common? It is pointing to something an identity has or a person has and no one else have it. That is the crux of authentication. So username and password, specific to a person. Unless you're sharing it with someone, it is very specific to a person. Fingerprint, unique to a person. Face, unique to a person. Biometrics, unique. PIN, just like password. Same with all these items here. This is possessed by an individual and it is unique to that particular entity. So that is what identity is all about. Now, all this has been compromised these days, especially username and password. Hardly anywhere you see just username and password. We have the two-factor authentication, two-factor, 2FA, or it is written as 2FA, like this. This is pretty common, especially if the resource you're protecting is very important. You need one more level of authentication. It could be a combination of one of these things. Say, for example, fingerprint and username, fingerprint and face, fingerprint and PIN, or any combination. But the most common, as you might have seen, is something to a different device. Say, for example, an OTP, which is just a number sending to a particular device, or an application which is running in a particular device. It could be a QR code, secret, unique QR code. For example, WhatsApp using QR code. So instead of username and password, an OTP or a QR code is considered more secure these days, because username and password has a demerit that it can be transferred very easily from one location to another. And there are so many additional behind the scene, untold mechanism. For example, Google, Facebook, Instagram, all these mass media platform uses the location of the device, the IP address of the user. They have different 2-factor, 3-factor, 4-factor authentication behind the scenes. They even monitor the nature of the mouse movements to understand if it is really a user or not. CAPTCHA. So many things are used behind the scenes to make sure that things are secure. So that is the crux of authentication, is you are using something specific to a person so that the system knows that it is the person sitting in front of the application or the service which it is authenticating. There is no need of any examples here. Gmail, Udemy, Instagram, Facebook, all these are examples. We've been doing that day in and day out. Now, what is common with all these things is once this verification is done, this part of the verification is done. So let's draw the verification part in a different color. So these are different things which is verified during the authentication phase. Once this is done, always this whole thing is converted to a number, a secret number, just like the session key of the TLS. So if you've been following my networking video, so you would have understood by now how numbers, certain numbers are important when it comes to something called context or session. So that is always the case with authentication as well. So for example, Gmail itself, if you look at Gmail, once you authenticate, once you type your username and password, they does all this checking, whatever they want. They send OTP to your phone, they send confirmation email to your other email, these, that, captcha, everything they does. But once you have done, after that, you don't need to do that again. Are they saving the username and password somewhere in your system? No, they are not. I mean, they do that for a different purpose, the password manager and things like that. That's not our discussion here. But for the authentication itself, they use a secret number. Normally, in the case of websites like Gmail or Facebook or Instagram, they save that in the cookie. In the case of an application like an Instagram app in the phone, it is saved inside the application storage space in which no other application can access. So we'll see where Chrome saves all these things. There's a folder in Windows. We'll look into that folder. But for the time being, what matters to us is that these things right here is always converted into a number. And mostly in the case of a website or an application, it is saved inside the cookies or any secondary storage which is considered to be secure. Very important point to note. We'll see that in the fiddler trace. We'll have a look at the fiddler trace. Now, why this is done? So this is where the knowledge of networking comes into the picture when it comes to security. So when you access your Gmail, suppose you're accessing your Gmail. So this is your Gmail, the Google server. You have logged in. So your login is happened. Google is happy with the OTP, QR code, whatever you have given. Google is happy. Google allowed you. Now, you need to assume that it gave a successful logon page. After that, Google has no connection whatsoever. The packets are completely independent. It is even not in the same TCP connection. So Google has no mechanism to understand that this request is coming from the same person unless they keep some number. Otherwise, Google will be asking username and password every time when you request, because all of those requests, most of those requests are happening inside different TCP connection. If you look at a Wireshark trace of a Gmail application or any Google application or Facebook or Instagram, you will see hundreds of TCP connections. There are some keep alive connections, but that's not the point here. As you might have seen, after logging into Gmail, even after you restart your machine, it works. You don't have to type your username and password after that, unless you log off, of course. How that is done? How Google maintains the context. The secret is this number we are talking here. So you send the username and password along with other things, whatever it asks. It returns a number very similar to the session key, the encryption session key, which we got within the TLS, but it is used for a different purpose. These numbers are very key in all kind of authentication. So authentication is standing on this particular backbone, this number thingy we are talking here. This number will appear in different shapes and sizes in different platforms. Gmail, I gave you an example which is there in the cookie, but there are so many other permutations and combinations. But always, whenever there is an authentication happens, if it is not asking for authentication again for subsequent request, it is definitely keeping a number, fairly big random number. That number can mean different things in different platform. All we know that it is a random number. And whenever you are not passing this number, for example, when you're not passing the cookie to the Gmail, it'll ask you to log in. For example, that's what happens when you open a Gmail from an in-private window. In-private window doesn't save the cookie from the previous session or the normal Chrome session. We'll see that. Because of that, there is no number present in the request. There is no cookie present in the request. And it'll ask for log on because the cookie is not present. So this is a very general concept. Authentication, the username and password, or any other identification you're giving is always converted to a secret big random number. Are we encrypting the traffic with that number? No, not necessarily. Mostly not, unless you have any specific purpose. That we do only for TLS. But this whole thing is going through TLS though. For example, Gmail is of course TLS. For example, from the networking perspective, there is an array of numbers starting from the MAC address, then the IP address, then the port number, These are all different layers of network actually. Port number, let's talk about Gmail in this case. Now, on top of that, so this is TCP, this is IP, and this is MAC or data link layer. On top of that, what we have, that is something we discussed, the session key of TLS. So the protocol is of course TLS. Now, on top of that, we have the cookie for Gmail or any other application you are using. So this particular cookie will determine which is the user. For example, the Gmail server is getting hundreds and thousands and millions of requests every second. And this particular TLS session is getting renewed every request. Every TLS session is different. This is getting changed. Normally, even this get changed. This also get changed. Everything changes. All these layers changes while you're using the Gmail. You may not be knowing how the MAC address is changing because you might be connecting to different Gmail servers. For example, one of your requests is going to one server, another request may be going to another server. It always happens. I think there is a demo in our networking training which demonstrate exactly this particular thing. They are not constant. The IP is not constant, so MAC is not constant. Again, I'm not getting into the details. Port is never constant. As long as the TCP connection changes, it is never constant. Session key, almost always when the TCP session closes, it closes the TLS as well. Again, there are exceptions, but mostly that's the case. Now, how do we know? All this is happening behind the scene. The user is not aware. We have not seen any of this happening when we use our Gmail. We upload, download, read emails, upload to Drive, Google Drive. All these things we do, all transparent to us. All these changes is completely unknown to us. The secret lies in this particular thing, this cookie. Yes, sometimes when your IP address changes, Google get a little suspicious and ask you to log in again. That is just a Google thing because it gets suspicious. Even though you have the cookie, sometimes it asks to re-log in when the IP address changes. Other than that, Google doesn't care. As long as you have this cookie, you're good to go. Which means this number is everything. Does that mean that if you steal this cookie from a system, you can get into the Gmail of someone else? The answer is yes. But it's not that simple. We'll see shortly why that is not simple and how the encryption is done in that particular folder and things like that. But at the end of the day, it all can be reversed. This particular cookie can be read. I'll show you some of the open source project which does exactly that, reading the cookie from the browser. So before we continue, let's have a look at this so-called number at least in the case of Gmail. You can take any other example if you want, but in this case, we are going to look at Gmail and we're going to see this particular cookie. So let me explain my setup a little bit first before we continue. I have a virtual machine running, which is a Windows virtual machine, because I want to isolate this whole traffic from the normal traffic I'm having, because we are going to run a fiddler in this particular machine. So let me clear this log and show you what we got. So this is a virtual machine. It's a Windows virtual machine, Windows 10 in fact. The laptop you're seeing the screen is a Windows 11 computer, but this virtual machine is Windows 10 if you want to differentiate between the VM and the laptop. But the fiddler is installed inside this particular VM. And of course we have added the fiddler root certificate to the trust store while we were installing fiddler, and fiddler is monitoring pretty much everything it can. Now what we have is a Gmail box right here. I'm going to press F12 so that I'll get the developer options. Instead of Chrome, I'm using Edge. I don't think it'll make any difference for our discussion. All I want to do is to generate some traffic, empty cache and hard refresh. This option will come only when you press F12 and you have this developer options turned on. Just I want to do a hard reload so that there'll be traffic. Now let's go to Fiddler and see some traffic. As you can see, there is traffic going to mail.google.com. That is the Gmail. So there is a lot of traffic. Let's take some of them. or one of them. So mail.google.com right here. So there are so many details. If you want, you can do it yourself and look at all the details if you want. But what I wanted to show you is the request headers. In the request header, we have something called cookie. So these are some of the secret numbers we are passing. So you can see so many cookies out here. So these are all secret numbers, means different things for Google. But have a look at this. And this is an authenticated session. That's why you are able to see the mails right here, right? It is already authenticated and you have the cookies. If you want, you can have a screenshot of this, or you can reverse the video later. But what I'm going to do is that I'm going to close this Gmail session right here, clean the log, and I'm going to start a in private window so that I will not have these cookies. So this is a authenticated one. This is how it looks when it is authenticated. So let me close this. I'm going to close this whole window. So one other thing is that even if we are closing these things, they won't go. They will connect back to the servers secretly in the background. So we need to observe it for some reason. Let's see, nothing is coming up. Looks like nothing is coming up. So I'm going to right click on this thing, new in private window. So it's an in private window right here. Let's see, something is coming up. At least nothing to mail.google.com, which is good. So let me clean this as well so that we'll have a clean log. So mail.google.com. So we have sent the traffic and this thing came up. As you can see, let's have a look, mail.google.com. And surprisingly, there is no cookie. There is no cookie in the request because it was an in private window. There was no cookie, no context, no number. The number which we discussed is missing. So what is the response we are getting? We are not getting a 200 anymore. We'll see a 200 before. We'll see a 200 later after the authentication. But in this case, we are getting 302. And 302 is a redirection. It is redirecting. Where it is redirecting? The server is telling us to go to accounts.google.com. Here you go. And then on, we are going to accounts.google.com. Again, it is redirecting to a different place. Again, here you go. Now, and finally, we are getting a 200 from the accounts.google.com. And if you do enough reverse engineering, you will see that it is this particular page right here. So one more interesting thing I'd like to show you here when we are talking about authentication is something in Fiddler. So this is kind of reinforce our learning of SSL TLS from the previous lesson. Also, I want to prove the point that the traffic through the TLS connection is not encrypted by the cookie and things like that, which I was mentioning in the theory part. So what I'm going to do is that I'm going to close this particular in private window and I'm going to start another in private window and go to Gmail, mail.google.com. Let me clean the Fiddler so that there is no stray traffic. So I have cleaned the Fiddler. Now I'm going to type an email and this is the email I'm going to go next. So in this case, I'm going to type the wrong password right here. So this is the password I'm going to type here. Anand, wrong password. I'll tell you why I'm going to type the wrong password. Even if I type the right password, what I'm going to show you is going to work exactly as it is. Now I'm going to click next and obviously it says the password is wrong. Now what's the point? The point is if you go to Fiddler right here and file, export sessions, all sessions. So what we are doing is we are exporting the whole traffic Fiddler has captured in curl format. If you're new to curl, don't know if you have dealt enough curl in this particular training, but I recommend the networking training if you're not. So curl script is nothing but text equivalent of these requests. I'm going to click next and I'm going to type Gmail hack and I'm going to save right here. Now this is a file we have simply saved and click on edit. It will open up in Notepad. This is a text file with just the curl command. It's a huge file normally with a lot of lines. Now, what is the password we've been typing? If I do a Control F, let's type the name Anand and As you can see, the password is right here. Anand, wrong password 1234. Which means that the password we typed is shown in plain text from the Gmail right here. So which means that once it is decrypted, everything is available in plain text. And that is how it is sent through the wire within the TLS session. So this is the risk we have taken while approving that trust certificate, which I mentioned in my previous lesson, to our trust store. We signed up for a big thing when we did that. Now, this is true for your bank account, your OTPs, every single traffic going from this particular computer right now. And this is precisely the reason why I'm doing it in a virtual machine, because there could be other things going in this screen right now, which I may not be even realize while showing you this. Otherwise, I have to mask everything. This is a virtual machine which I don't have any private data. Otherwise, you may see my bank account probably here and password. We never know. But the point is, Fiddler is decrypting every single thing, including your password. If this password was the correct password, it would have come there. You can test that yourself. I'll leave that as an exercise to you. Now, can you write something like Fiddler and transfer this kind of things remotely? Definitely yes. That's why you should not allow anyone to install anything in your system. Right now, Fiddler is very neat. But at the end of the day, what it takes to decrypt all your traffic is a proxy and a certificate in a trust store. That's a point we are trying to mention here. And no cookie, no two-factor authentication is going to save you. Everything is getting decrypted. Once the session is established, it is gone. All the cookie you will see will be there in this particular session. And that cookie can be replicated in a remote location. That's why services like Google has some kind of IP address checks every now and then. But I have seen Gmail trust cookies pretty much from anywhere, because I travel to a lot of countries every now and then. And in the lockdown sessions, Gmail never used to ask me password. It just trusts my cookies, which means through a Fiddler session or a proxy, if my cookie is compromised, it is a very bad thing to happen. Now I'm going to close this and I will start a normal session and we will see the cookies once again before we wind up this particular demo. I'm removing everything, all gone. It's a normal browser, again mail.google.com, Gmail. It should directly go. As you can see, the cookies are already available. Now let's have a look at the traffic in the Fiddler. So mail.google.com. You should look at request headers. The response header is also there. If you're looking, what matters is the request header. Response header is the header which is coming with the response from the server. But feel free to study everything if you are curious about it. But as you can see, these are the cookies we've been talking about. I'm not saying that all this is part of authentication. Half of the things Google must be trying to steal your data. Doesn't matter. It's all encrypted or it's all cryptic. We can't make much sense out of it anyway. Whatever they are doing within the server, only they knows. Doesn't matter to us, or we doesn't know. We can poke around for sure because we have the number and things like that, but ultimately it's their business. And there is no much set standard for what are the cookies to put and things like that. But for us, this whole thing is a number. This is the number we've been discussing in our block diagram. That's the whole point. After authentication, it has converted into this big number right here, or a group of numbers. But for us, it is just one number from the discussion standpoint. So one of the things which we would like to mention here is that if you ask me, if you copy this entire cookie and if you push it with a request, will it work? There's a good chance it may not work because these cookies may have some kind of checksum of the request data as well. If you want to hack Gmail like that, you need to understand how it works. You need to reverse engineer all their JavaScript code and understand how it works and how these cookies are being used and handled in the client side before you do that. Sometimes it may work, but mostly it may not, because that is what I would do. I would put some checksum of the entire request so that I want to make sure that no one has tampered with my request. But I don't know if they have done it. Doesn't matter. The idea of copying these things may or may not work. But it'll give you a good start. If you have this thing getting into Gmail of someone, will not be that difficult because it'll be a common algorithm used everywhere. So coming back to our block diagram, what is the purpose of authentication? It's all about determining an identity across the network, making sure that a person is the person whom they are claiming to be. That's the whole point of identification. In real world also we do that. We have the ID card, we have the license, we have the passport. All these are similar things. So what Google must be doing with this particular number? Let's have a quick discussion on that. So we have the number, which is the cookie in this case. And this number is obtained from Google or Gmail in this case, or whoever is authenticating us. Now, they will have all the data. That'll be like a primary key to a table. For in this case, Google will have all our Gmail, all our private data connected to this number. So it'll check whenever a request comes, what is this number right here, the cookie, and based on that number, it'll return the correct information, correct mailbox. So that's why I said, if you give a different number of a different person, you will get a different Gmail box. So that's the quick working of the server side. So let's go through the authentication page in Wikipedia. So authentication, this is a very general article as far as I can see. Whatever we discussed is very specific to digital authentication, especially the number thingy I told. That's very specific to our computer world. But authentication is a very generic concept, as you can see here. By the way, one of the most important type of authentication is mTLS. Now that I'm seeing it right here, let me quickly explain that because it was not there in my list. It is one of the most important type of authentication. So let's erase this particular diagram. So some of these kind of topics will come every now and then when we review this and that. That's why we look at Wikipedia pages, just to make sure that we covered everything. Normally, I discuss the main points and some of the details I skip. But in this case, mTLS is definitely worth discussing. mTLS. We had a quick discussion on this before, but we have not recognized it as an important authentication mechanism. So let's see how it works. It works exactly as the normal TLS. No much difference. So what TLS does? TLS verify the server. So we have Alice and we have Bob. And this is the internet. And we have Eve present in the internet. Remember, Eve is very smart. She knows every single hack in the whole world. She's probably the most smart engineer out there. Now, with TLS, we have discussed in detail how Alice verifies she is talking to Bob and no one else. With the public key of Bob, which is trusted a root within Alice's system or Alice's application. She has a trusted list of public keys available, and that public key will tell whether she wants to trust Bob or not. Unless, of course, the public key itself of the Bob is known to Alice, which is normally not the case. But does Bob care about to whom he is talking about? Does he know if he is talking to Eve or Alice? Now we are talking about authentication. The answer is no. TLS doesn't verify the client by default. TLS only verifies the server. Now we are talking about authentication, which is always about verifying the client by username, password, by cookies, by all different means we have discussed so far. And mTLS, and there are some other technologies similar to that, SSH for example, which we authenticate to a Linux terminal, SSH port 22. All these uses similar mechanisms like mTLS. So how it works? In this case, Bob also does the exact same kind of verification. Bob has a trusted list of public key, and Bob asks for a client certificate. Bob asks for a client certificate to Alice. Hey Alice, I need a client certificate. If Alice is not giving a client certificate which is trusted by Bob, just like Alice was doing so far in the case of TLS, if Alice is not giving a trusted certificate, just like the server, the TLS handshake fails. So Alice should have a private key. Normally, in the case of TLS, Alice never has a private key. All she does is verifies what Bob's give. But in this case, Bob wants to verify whom he is talking to. That's where the mTLS comes, the private key. So here the private key used like a password, but more secure than that. You need to have that proper private key, which is trusted. The public key should be trusted by Bob. And most cases, this is not a public key trust verification happens here. It is normally a CNAME verification. Definitely, it can be configured in different ways. Different rules can be put in servers like Nginx, for example, to do the mTLS. You can do the CNAME verification. You can do the trust verification and things like that. There are some weird limits as well with mTLS for trust verification. So I recommend do not do trust verification with mTLS. If you're using mTLS, always use CNAME verification. It's very important. It's a security practice. Don't do trust verification. If you want details, feel free to contact me. I can tell you all the details, but otherwise it is slightly outside the context and scope of this particular training. But always there's CNAME verification, which means that check for if the CA is trusted, as well as the public key is a specific public key and the CNAME is a particular CNAME. Not just verify the trust relationship, which can be done as well in the case of mTLS, like trusting all the certificate coming from a particular CA. So that is not really saving the purpose of mTLS. This is more harder to implement, but that's what I recommend if you're using mTLS. So you will authenticate Alice, making sure that Alice is Alice. There is a lot of demerits with mTLS, which is very hard to manage mTLS unless you have a proper system. It's very hard to manage, but it's relatively very secure when it comes to username and password. But it's very static and it is fairly difficult to revoke. A lot of different issues are there, but mTLS is another way of authentication. The reason why I'm stressing on mTLS is because you might not have been familiar with this particular method of authentication. You might have seen face, fingerprint, PIN, username, password, OTP, all these things you might have been experienced, but mTLS, not sure how many of you have experienced. Now, going back to the article we've been looking at, we were looking at the Wikipedia article. Let's get back to it so that any topics like this is missed. As you can see, this is a very general article. It is talking about all kind of different authentication in the real world, not the digital world. So these are some of the basic things: knowledge, ownership, inheritance, pretty much everything what we just discussed. DNA sequence, all this kind of different things you possess. Something the user knows, something user has, something user is or does. For example, in one of the banks here, used to verify my voice. In fact, it's doing that even today. It asks you to read something so that it verifies my voice. I don't know how secure is that in these AI days. I don't think it's very secure, but it is what it is. So that is what someone does, if you're wondering what does really means. Single factor, multi-factor, nowadays everything is multi-factor. So many types of authentication it's mentioning. You can read about it. Man in the middle attack, TLS, man in the middle attack. TLS is always about preventing man in the middle attack. For example, in the case of Gmail, first you establish a Gmail TLS session with the Gmail server. Then only you start passing all your username and password and things like that. So that's how you counter man in the middle attack. Then there is this QR code, all different sorts of things. It is talking about authorization as well, but I'm pretty sure there is a different authorization article, which is another big topic. Access control, again, part of authorization, I would say. We'll discuss all these things in one shot, probably not here. One particular protocol worth mentioning in the context of authentication is probably SSH, the terminal access, remote terminal access in Linux, which uses port 22. It is very similar to mTLS. Only difference is that in the case of SSH, the public key is one single key normally. SSH uses all kind of authentication these days, including Active Directory and things like that. There's a lot of modules available, but we are talking about the key-based SSH authentication, which is one of the most used SSH authentication, which is very similar to mTLS, just that instead of using any CA or anything fancy, all you're going to do is you're going to tell the SSH server which public key it is going to trust. No CA business. You configure the public key and you access the SSH client using the private key. Let me quickly draw the diagram because SSH is an important protocol, and I'm pretty sure if you have not done it already, you will do it in future. SSH key configuration. So I don't want you to get confused. Some people are confused where to put the private key, where to put the public key, etc. So let's have a quick look with the help of the diagram. So again, we have the client and the server, the SSH server, or the SSH daemon, SSHD, and something like PuTTY or SSH or WinSCP or SCP, some kind of SSH client. It's all uses the same thing. So what we are going to discuss here is key-based authentication, key-based auth. The reason I'm stressing on this particular piece is that SSH can be done in multiple different mechanisms. In the server, what we're going to do is there'll be a configuration within the server which saves the public key. So public key, you will be putting it in the server. This is basically telling the server directly what public key to trust. And there will be a private key in the client. Always client will have the private key because that is what is having the secret. The client is going to have the secret. Using this public key, it will connect, and this public key is trusted. There is no business of CA. There's no trust thingy normally. And if the key is matching, it will allow the connection. So this is the way traditionally SSH works. SSH has username and password as well. You might have seen that, username and password. But the secure way to use SSH is considered to be the key. As well as you can use automation using key because you don't have to type any passwords. Now, before we wind up the session, I want to discuss the list of entities which can authenticate. So that is another thing worth mentioning. For example, a human being who sits in front of a computer. But that's not always the case. Authentication can be done using softwares as well. Let's see potential list of it. Let's erase this diagram and take a new one. So the question we are going to address here is that who can or what, can be who or what, can authenticate. So this is the question we're trying to address here. This is an important thing because a lot of the times people think that only humans can authenticate, which is wrong, and that leads to a lot of complications. Obviously, human users, I'm going to call it users, end users. Definitely users can authenticate. Users. Another is systems. Say for example a virtual machine. Virtual machine can have an identity by its own. For example, an EC2 instance can have a profile within AWS. It's called instance profile, and it becomes an identity. User can have all the things we discussed, username, password, and all sorts of things. And mostly this kind of things come up with a number. They already have that number we've been talking about. Most of these things will have a number, a virtual machine. Another is a software with a pet name called service. Software, any code, any piece of code. Mostly they have something like an API key. Again, some number. It has a specific number or a key or an SSH key or even an mTLS. Basically, a number. It'll have a number, secret number, random big number, like the cookies we have seen. So sometimes this is called service principal. Principal is normally referred, it's more of a Microsoft term, date backs to the early 80s at the time of Active Directory when it came to the picture. We'll discuss about Active Directory and a little bit of history of role-based access control. History as we know it, or as I know it. Probably there is more history to it. It doesn't matter to us. But the name principle, this particular word right here, this normally refers to the Microsoft documentation, service principle. It is kind of referring to who can behave like an identity, who can authenticate. So virtual machines, software, and human users. Pretty much anything which comes up with a number within the network. So the other side, so there is one side where the user side and another is the service, say for example Gmail. So all we need for this authentication to work is the number. There's a number, specific number like that cookies we have seen. So whoever provides this number through this network, they can potentially authenticate and access this particular service right here. It can be anything. It can be a human being. It can be a software. It can be a virtual machine. It can be something else. As long as it comes with this number, this service will allow it. So that's the idea. But these are the normal items. But you will see a lot of different names and resources and all different things. But be aware that it is all about the secret number it is transmitting. So we have seen the basics of authentication, some of the challenges we face for the authentication, and the mechanisms we use to authenticate, to prove your identity. Now there is more to it. Authentication is just one of the things. There is more to it, and we can discuss that in the coming lessons. Thank you, and see you in the next lesson.